Let's compare and contrast between subjects ANOVA and observational modeling by analyzing data from this fascinating study published in 2006 by Hunchins et al. On interidentity amnesia in individuals who have been diagnosed with dissociative identity disorder, or just DID for short. Now, this used to be known as multiple personality disorder back in the day. Now, in this study, the independent variable was comprised of 4 groups. As you can see on the screen here, we have 19 DID patients, 25 controls, 25 simulators, and 25 guessers. Now, the simulators were individuals who were taught about DID, and then they feigned that diagnosis while completing the procedures in this study. Now, the primary idea here, the goal of this research, was to figure out whether or not the DID individuals would have cross-personality memory. So in other words, would one personality be able to recall what another personality had previously remembered? And so the dependent variable, the outcome variable, was number of remembered words that were successfully recalled by the other personality or successfully recognized. And the range there is 0 to 15 words correctly recognized. If you want to know more about this research, you can read the papers that I've got listed on the screen here. Now, to analyze the data within ANOVA, we would begin by computing a table of means and variances, as you can see here. Now, the overall goal of the analysis will be to partition this total variation in the recognized words into 2 independent sources. We have the sums of squares between, which is primarily concerned with the variation between the means, as you can see in the formula here. And then you have the sums of squares within, which is primarily concerned with the within group variances. As you can see with the formula, we're just weighting and summing those within group variances. Now, if we run through the computations, we can see the sum of square values here. We can divide those results by the degrees of freedom to get these 2 mean squares values, which are essentially variances. That's why it's known as analysis of variance. And then we take the ratio of those 2 numbers to get the F ratio, or the F value. Here it's 247.297, which is an astronomical value. This is a huge F value, and not surprisingly, it is statistically significant, p less than 0.001. So if we're using 0.05 as our criterion, for example, we exceed that by quite a bit. Now, of course, if we are taking note of that p-value, then we are engaged in null hypothesis significance testing. And here we can see the null hypothesis that posits that the 4 population means are exactly equal, and then the alternative hypothesis that posits that the population means are not all exactly equal. And as we saw with this massive F value and small p value, we would reject the null hypothesis and conclude the alternative hypothesis. And in a published paper, we might write the words statistically significant. Now, let's also remind ourselves while we're here of the various assumptions that underlie null hypothesis significance testing, or that p-value. Now, if you violate one or more of these assumptions, that's detrimental to the p-value and therefore to your conclusion of rejecting the null hypothesis. Now, some would argue that violating one or more of these assumptions might also just invalidate the p-value altogether, for example, violating the random sampling assumption. But we'll just let that go for now and move on with the analysis. So we could plot the means as we see here, and the control group recognized on average the most number of words. You can see some variation here in the means between the other 3 groups. We could plot standard error bars in here as well if we wished. We could also move on to specific hypotheses, which is usually where all the action is in the analysis of variance. So here I have one example of comparing the first 2 population means for the null hypothesis, and then inequalities one way or the other for the alternative hypothesis. This is what's known as 3-valued logic form for these hypotheses. As one example of an analysis for these pairwise comparisons, we could look at these DID patients versus the simulators, and we can see that the p-value here is 0.07, so it is not statistically significant at the 0.05 level after using this Tukey's HSD adjustment. Finally, we could compute the effect sizes and confidence intervals. So here I've got eta squared for the omnibus hypothesis. We could compute little f as well, and then here we see the 95% confidence intervals for the particular means. So what we've done with the ANOVA, we have focused on partitioning variance. We've based the analysis on means and variances. Our goal was to estimate population parameters, as we can see with the null hypothesis here, and we relied on statistical significance with its many assumptions in rejecting the null hypothesis and concluding that the population means are not all equal. Now, by comparison with OOM, we're going to focus on patterns within our data. We're going to analyze individual responses rather than means and variances. And our goal is going to be to find a person-centered causal explanation of the data, or the patterns within the data. And we're going to use a distribution-free randomization test to replace that traditional p-value. So we could begin by simply looking at our data, giving it the eyeball test. So here I have what's called a colorless multigram. And you can see I've just set up histograms for each of the 4 groups, and I've set them side by side. Now the numbers in the bars represent the frequencies, the head counts. And so here are all of the data presented in one picture, one nifty graph. So we can see, for example, 3 words were recognized, or 7 individuals recognized 3 words in the DID group. We see 2 individuals in the simulator group who recognized 3 words, and 2 individuals in the guesser group who recognized 3 words. None of the individuals in the control group recognized 3 words. We can also just see some separation here between the groups just by eyeballing it. Obviously, the controls recognized a lot more words than the other 3 groups. In fact, there was only one bit of overlap here between the 2 distributions. An individual there recognized 9. One of the guessers actually guessed 9 correct, which is pretty unusual. We might see a little bit of differentiation between the groups here as well, just overall. Now let's add some color to this graph. So now we have what's called a multigram. And what I've done here is used a Bayesian light classifier to classify the individuals into one of the 4 groups. Now the analysis works by looking at the overall pattern in the data of the recognition scores, and then it classifies each person into a particular group. And then that person is either correctly classified or incorrectly classified. So for example, again, for these 7 individuals in the DID group, they were classified by the Bayesian light classifier as DID patients. And in fact, they're DID patients. So the 7 individuals here, the bar is green. By contrast, we have the 2 individuals here who are simulators. The classifier indicated that they should be DID patients, but they're not. They're simulators, so they're incorrectly classified. Similarly, for these 2 guessers, they're incorrectly classified. Now, if we tally all of the numbers in the green bars, we arrive, and turn that into a percentage, we arrive at what is known as the percent correct classifications index. And here it's 74.47%, indicating that there appear to be general differences among the 4 groups here in terms of their recognition scores. Again, we can see it with our eyeball as well by looking at the multigram. Now, we can subject this PCC to a randomization test, and that yields what is known as a chance value in the OOM software. So what we do is we just randomly shuffle the data over and over again, and every time we compute a PCC index, and that creates a distribution of randomized PCCs. Then we compare the actual PCC to that randomized distribution of PCCs. And in this case, with 5,000 randomizations of the same data, not 1 in 5,000 times were we able to find a PCC of 74.47% or higher. That gives us a chance value, a C value of less than 0.0002. Now that indicates then that we just can't randomly shuffle our data haphazardly, aligning the data, and come up with a PCC value of at least 75 or approximately 75%. And therefore we rule out physical chance as a likely explanation of the pattern in the data. So in this way, we've replaced that p-value with a relatively assumption-free randomization test. Now we can move on and do specific pairwise comparisons. And here I have lined up or compared the simulators with the guessers. And you can see the overall pattern results here. The simulators are recognizing fewer words typically than the guessers. You can see we have quite a few green bars here. Convert that to a percentage, and sure enough, we have a fairly high PCC index here of 80%. So our eye is telling us there are some robust differences here between the 2 groups. The PCC is backing that up with 80%. The randomization test gives us a chance value less than or equal to, in this case, 0.0014. Again, then we would rule out physical chance as a likely explanation for the pattern that we're seeing in the data here. So the next goal then is to explain the pattern that we see in the data since we've ruled out physical chance. And this needs to be a person-centered causal explanation. So what is it about the simulators? What is the mechanism that is operating here to generate most of the values here between 0 and 2, compared to the mechanism for the guessers that is generating results of 3 to 9. And again, this needs to be a person-centered mechanism. What is it that is causing the pattern that we see in the individual observations here in the multigram? Now, Hunchins et al. Did not present a causal diagram for their results, but it might look something like you see on the screen here from this paper in 2017. Now, this is for a different study, so I'm not going to go into details of what of this particular diagram, but the goal here is again to explain the causes and the effects, or to map out in a visual presentation the causes and the effects underlying the data. And again, it needs to be person-centered. We refer to these as integrated models in observation-oriented modeling, and these are very difficult to put together. The analysis might be fairly easy, but coming up with a true causal explanation for what you're seeing in your data, that's the difficult task, I should say. And by the way, you generalize beyond your particular sample through your causal model. What makes you think that your results are going to generalize to a new sample? It's the causes and the effects, right? The causes that are underlying the pattern in the data. That's why you think they're going to generalize. Now, the only way to test that out is to go get another sample. The chance value isn't going to help you with that. You've got to go get another sample to actually see if your results were generalized. But you think they're going to generalize because of the causes that are at work generating the pattern within the data. And so we've analyzed our data without computing a single mean or standard deviation, without losing sight of the persons in the study, without making various assumptions to get a p-value, without referring to an undefined or imaginary population, without worrying about outliers or irregular cases. If I go back to the colorless multigram, for example, I see these two individuals. Are these outliers? Are they influential cases? Do I need to worry about these individuals perhaps unduly pulling the mean up? I don't need to worry about that in observational modeling because I'm not analyzing means and variances. I'm analyzing patterns of individual responses. So in closing, or as a final word, I should say, there are other ways we could have analyzed these same data in the OOM software. And each of those approaches is similar in spirit to the analysis presented in this video.